So welcome Indrajit again to Self-Start webinar on recursive neural tensor networks. I'll hand it over to you now and you can take over the charge.
All right, thanks, Vivek. Um,
Go ahead.
so let me share the screen. I hope it is visible.
Yes, it is. Go ahead.
Okay, so we'll start with the session with recursive neural tensor network. So I hope my voice is audible properly.
Yes, please. Go ahead.
Okay, so to start with, I mean, there is a purpose that we actually learn about certain algorithms in deep learning or normal machine learning algorithms. So one of the aspect of learning this recursive neural tensor network is to know uh, what exactly a recursive neural nets does. I mean, there is another neural network you might have heard about, like RNN, so which is very popular with that is basically recurrent neural network. With recurrent neural network, there is another way that we actually define or try to solve NLP problems. So one of the important aspect of these algorithm is recursiveness of the model. So our primary purpose is to find the compositionality or the meaning of a sentence. So primarily we solve multiple NLP problems. For example, here I have considered sentiment analysis as an example, and how recursive neural tensor network helps in solving Twitter sentiment analysis or any social media data analysis for finding the sentiment. So a sentiment can be positive, negative, or it could be very negative or neutral, or it can be very positive. So there are 5 different types of sentiment that can be find out from these algorithm. Normally people do the sentiment with either positive or negative. So we will see how these algorithm helps, and we can also have some uh, discussion at the end that whether this network is the best, or if there is any other the latest neural models which are much more helpful for finding this. So there are obviously some pros and cons for different types of neural networks, and we should be able to find out what exactly is the use case and why we should be using a particular algorithm. So let's get started. The original paper has been published by Richard Saucer and from Stanford NLP group. So this paper has been published in 2011, around 2011 to 12, and uh, the most of the publications has been done by Stanford, and they have the very famous library you have heard about, Core NLP. So this is also built on RNN, I mean with RNTN. Okay, so let's get started with sentiment analysis. So what we actually find out in a sentiment, we see basically a feature of natural language processing and text analysis, and we do identify the emotion present in a set of case and data by classifying sentiment polarity. So basically it could be positive, negative, or neutral. It could be very negative or very positive. So what is the challenge in finding this kind of analysis or sentiment from social media data? So I mean, there are different types of challenges in terms of finding the compositionality, basically meaning of a sentence. So what we mean by meaning of a sentence? Meaning is the information that a sender intends to convey, right, or does convey to a receiver. So it is dependent on what the sender is, what type of sender is, or if I'm a writer, if I'm writing something, what is my intention of writing, towards whom? Is it towards a person, or towards an object, or towards some particular topic? So to find the meaning from sentence, it is really a challenging task. And so we will see how these algorithm helps in finding that, instead of only getting the words negative or positive. We actually try to find out a global meaning from the word or the corpus. Okay, so sentiment analysis of social media, like process of computationally identifying and categorizing opinions expressed in a piece of text. So especially in order to determine whether the writer's intention is towards a particular concept, person, topic, or product, etc. If it is positive, if it is negative, or neutral. So with Facebook public messages, there could be different types of emotions, different types of context, that people want to mean something, but people get something else. So it's really difficult to get the meaning of a particular post, or even a Twitter post is very difficult to get. So here you see, as an example, like only the Twitter tweets, right? There are only 1% of the API is available, as for the public, but most of them are not available to public. So how actually we do access to these kind of valuable data and find the the meaning, or even use case scenarios? So this is the GitHub link that you can find this core NLP library, a toolkit, and it can be used for multiple purpose. So this is basically written in Java and licensed under GNU public license. But this has a Python version as well. You might have heard about Stanford NLP, so you can try that as well, and see if how it helps in finding the sentiment. So this core NLP library, it uses recursive neural tensor network. So to go ahead with that, let's first find out what are the existing methods, and what are the challenges before we use, or go through RNTN. That will clarify our understanding of finding such problems, or finding the solution, or basically the compositionality or meaning from a particular sentence. So one of the things that we normally do is one hot encoding. So I hope everyone heard about this. Let me clarify on this. So basically capturing a simple relationship, such as determining that the words dog and cat both refer to animal that are often discussed in the context of household pets. So here we do not get any kind of similarity or a meaning from a particular word. So let's say, for example, if I say cat, right? uh, and my word vectors are, let's say I have cat and dog. Along with that, it could be any other animal, but for, let's say, I have cat, dog, and um, elephant. Let's say I'm not going to write that. So I will have, let's say, if it is existing with the document, I will put a certain one hot encoding. 0 means doesn't exist, right? So all are different. So here, this way we do a one hot encoding, but if we do a dot product of these vectors, we do not get anything. We basically get a zero value, because all of these are different, and we cannot actually find any similarity between these words. So basically do not capture any syntactic or structure and semantic or meaning relationships across collection of words, and therefore represent language in a very naive way. So we should be able to find out some better options of these. So what are the better options? I mean, So we have something called bag of words, right? So let me erase this, and let's go ahead. Okay. So bag of words are basically a collection of words or documents, so from a particular corpora. So if I have a document 1 and document 2, a quick brown fox jumped over the lazy dog's back. So here this document 1 consists of few words, and document 2 also consists of few words. So what we will do is we will collect all of these words, and we'll see how many, I mean, what is that document, if it is existing in that particular document or not, right? So in document 1, if it exists, let's say back exists in document 1, I have 1 for that. Brown exists in document 1, I have 1 for that, right? Come exist in document document 1, no. Come exist in document 2, so I have 0 for that, and document 2 I have 1 for come, right? So this way we basically build a bag of words model, and we find that how many times, not how many times, we do not get a frequency of the terms, but we get the vectors that the word occurring, right? So but it again, it doesn't solve the purpose. We basically don't get any meaning or any kind of compositionality from these kind of models. So going forward, we'll go on into the deeper sections of RNTN. So before RNTN, we will also talk about RNN, the existing model, and what it does. So there would be a better understanding of the models and their correlations, right? So word vectors also one of the other NLP problems that we try to solve with the words. And but here also, if you see, I have some sentence like I love programming, I love math, I tolerate biology. So I collected those words and put them in the word vector, and we see that if they are occurring. So since here, if you see here, programming and math share the same co-occurrence values, right? And they would be placed in the in the same format. So meaning that in this context they mean the same thing, or pretty much the same thing, but we could not actually get the actual actual compositionality from these kind of settings as well. So and next, I mean, it's computationally expensive, right? It creates a huge matrix, and since we are taking about a very high dimensional space here, and high dimensional space, and therefore we need a technique that reduces dimensionality for us with the least data loss possible, right? So increase in size with vocabulary. If the vocabulary size increases, if I have let's say 10,000 words in a particular document or corpus, it will increase to 10,000 vectors, right? So it is very computationally it would be very high, and subsequent classification on models have sparsity issues, of course, and models are less robust. So these are the problems with the word vector models. So for this, we already have some solution. I mean, people have heard about SVD. So we'll just quickly see what is the solution. So the idea here is to store only the most important information in order to have a dense vector, or eliminating as much zeros as possible from the sparse matrix. So with low number of dimensions, right? So if you see here, here SVD is one of the solution. So just quickly go over that singular value decomposition, or SVD. So what it does is, the primary purpose is to reduce the dimensionality, right? So we use this kind of algorithm like SVD, where m into n is a matrix. There exists a singular value decomposition of m, right? So U is an m into m unitary matrix, basically a left singular vector, and sigma is a m into n diagonal matrix with non-negative real numbers, along with V is an n into n unitary matrix again, so right singular vector. So if you see as a diagram, right? So I think I did not keep that, but normally it will look like m into m and m into n and n into n unitary matrix. So just to understand, I mean, even if with the singular value decomposition after you reduce the dimensionality, whether it solves the problem. So basically computational cost scales, I mean, quadratically for n into m matrix. Again, there is also a problem with the cost, and bad for millions of words or documents, hard to incorporate new words or documents, and different learning regime than other DL models. So this is again not a very good idea to use, or use SVT to reduce the dimensionality. So further we have these new techniques like word2vec and skipgrams and glove. So this has been also used with our training models, but we actually do not see that everything is basically this is solving all the problems, right? And we do not get the context. Like both CBOW and skipgrams are predictive models, and in that they only take local context into the account, but they do not take the global context. So that is also one of the challenges with word2vec model. And glove also embeddings by contrast leverage the same intuition behind the occurring matrix used distributional embeddings, but uses neural methods to decompose the co-occurrence matrix into more expressive and dense word vectors. Now, so as I told you at the beginning, the primary goal is to find the compositionality or meaning of a particular sentence. So the meaning of it words or the rules that combine them, right? So this is that is the purpose. So word to vec skipgrams might solve a bit of problems with the word vectors and finding the the uh, the the local context, but we do not be able to solve the global context for a word or a sentence, right? So along with that we need something better, right? So for another kind of algorithm that we normally use is word embedding matrix, right? What is an embedding matrix? Example, take three similar phrases: when the worker left, when the fisherman left, and when the dog left. So here if you imagine, don't so we don't know worker and fisherman and dog, right? What they mean. So in fact we don't know any of the words, but can easily tell that the phrases are identical except for one word, right? So worker, fisherman, and dog. So since the context are identical, we could extrapolate that some similarity exists, right? We can only extrapolate that there is some similarity between these words, but by applying this idea to an entire corpus, we could define the relationship between the words, right? We can actually define that there is some relationship between these words. So when we apply to a corpora, so word embeddings normally looks like this. It's a vector, and conceptually you get a words vector by left multiplying a one hot vector, right? So this is normally in word embedding matrix does. Now whether that solves the complete problem of finding the meaning, no, it could not find the again the global meaning or compositionality of a particular corpora or document set, right? So we have these so for with to solve this problem, we already been used a lot of algorithms with that. You can I mean, you might have heard about RNN, RNTN, LSTM, and now recently we have BERT, ELMO, right? So these algorithms are much more advanced, and they basically use the similar kind of concept. With that, they have some additional methods, which basically like let's say, for example, with LSTM, if you use um, um, the attention, right? So that solves a lot of problems. So that gives a better compositionality. We'll talk about that at the end of this session, but as this session is to only discuss about RNTN, so we will focus on that and what exactly it solves right here. So before that, with recurrent neural networks, right? If I say recurrent, right? So uses a sequential inputs where the time factor is the main differentiating factor between the elements of the sequence. So here time is the main factor, right? So if you understand from the recurrent concept, right? So recurrent means it actually at time t there is some word that is coming into the network, and at let's say there is a state of h of let me bring the pen here. So let's say I have ht equals to some function with parameters, let's say some function with parameter w with a old state, let's say ht minus 1, right? And I have an input vector at some time step t, let's say that is called as xt, right? Here you see x0, x1, x2, xt. So these are the that states that we actually we pass into the next layer, and we find the we try to basically find the hidden vectors here, right? So to get a non-linearity in the system, this recurrent neural network I mean takes an input as a word, right, as a word or a character, and it finds the meaning based on the timestamp or the state of that particular hidden layer, right? So we solve that using a recurrent neural network, but there is some like I mean it requires a parser to get a tree structure, right? Here I mean with the recurrent, right, it looks like I mean cannot basically compute the phrases within a prefix context, or often captures too much of last words in the final vector, right? So that is also one of the challenge with the recurrent neural network. So we'll see with the next slide. Let's say, let me know if you have any queries in between,
So
or we
none
can
as
take
of
the
now.
question. Yeah,
None as of now. So continue.
okay, sure. So with RNN, right, it basically have this kind of structure, if you see, right? So here normally if you see with the F, right, so P1 is the word composition here, and B and C are the vectors, right? So B and C are the vectors here, and D into 2D is the weight matrix here. I mean basically the model's main training parameter that we use here, right? So if you D into 2D, if you see here, so that is the weight matrix, right? And F is the hyperbolic tangent, right? Hyperbolic tangent being used here. So with the weight matrix, I mean we are applying this weight matrix D into 2D weight matrix on the vector, right? And we get a certain score. So that based on that score, we actually find out whether what is the what is the weightage that we give for a particular word, and based on that we find the meaning. So now with RNN, this is the normal structure, and we basically train the sentences based on this, right, using the tanh function. Now problem with RNN is that in the standard RNN, the input vectors only implicitly interact through the non-linearity, right, squashing function basically. So a more direct, possibly multiplicative or interaction would allow the model to have greater interactions between the input vectors, right? So that is one of the challenges with RNN, and we need to find a solution to that. So instead of recurrent neural network, we have recursive neural models. Like here is example not very good. So very good we will take, and then we will get a we'll get a vector for that, let's say parent p1 to that, and for whatever value we get from that, we apply that p1 and we take to the next layer. So it is basically a hierarchical structure, a tree structure, basically a binary tree kind of format, right? Here, so it has three nodes, one parent and two left and right child nodes, right? So these structure is followed with the recursive neural model, but with RNN, right, normally we do not follow any structure, right? So this is so if you see here, I mean say with a recurrent, right, just to this is very important to understand here with the recurrent and recursive. So recurrent both has the same name as RNN, right? So recurrent neural net and recursive neural net, let's say. Okay, so with the recursive we have a tree-like structure, right? A tree-like structure like this here, if you see here. With the recurrent, we do not have a tree-like structure, but it is just a layer after. I mean, basically, we place the hidden layers, and we find the context based on the timestamp, right? T. So it looks like with the RNN, right? It will look like this. Okay, let me quickly draw it. So anything with the word vectors, let's say with the hidden state, sorry, it's not getting. So we see like this, some values with the word vectors, and then add some feature with the X, right? So let's say I have something called the cat is, right? So for each x t till xt dot any word, we actually pass this to the next layer, and we find at time t and t minus 1 what is the context, and we get the weight matrix, right? So this is with RNN, recurrent neural net. With recursive, we have a tree-like structure. We find, say, not very good for very and good, whatever the weight matrix we get, we pass it to the next hierarchical node, and we find that value, and based on that, the from going from bottom up, we get a particular value to that, right? So is it clear? Okay, so next is we'll okay. So with RNN, we have something called matrix vector RNN. So matrix vector recursive neural network. So we did not yet introduce RNTN here. Just trying to get the other algorithms that has been used and what are the challenges with them, right? So with MVRNN representing every node in the parse tree, both has a vector and a matrix. So what happens? What we do here is we actually present the parse tree and the same recursive format, but here we have a vector and a matrix, right? We use both vector and a matrix combination in this recursive basically neural network, right? MVRNN. So MVRNN basically uses a matrix and a vector both. So B and C here is again a word vectors, right? So capital B and capital C are respective matrices. So here capital B and capital C are matrices, and small b and small c are vectors, right? P1 is the resulting vector. Small p1, if you see here, is the resulting vector, and the capital P1 is the respective matrix. So we passing this to hierarchical nodes, and ultimately we get the root node where P2 and P2 is the resulting vector, and the P2 capital P2 is the respective matrix. So this is how we actually calculate from a particular given sentence. So right, so the problem with this is model is the number of trainable parameters, right, becomes too large as the vocabulary size increases. So if the vocabulary size increases, my vector and the matrix will be very high, and that is computationally expensive, right? So that is one of the challenges with the MBRNN model, right? So size of the parameter becomes very large, and it depends on the size of the vocabulary. Solution is use a simple powerful compositional function with a fixed number of parameters. So instead of the parameters as a variable, right, we should have something where the parameters are fixed, right? So we can get much more in a simpler way to find the composition. or compositional meaning from a vector. Sorry. So that's why I propose this. Why RNTN? The algorithm uses a powerful fixed size compositional vector representations or phrases of variable length and syntactic type, which only takes the word vectors as arguments also. And say also the model is not parameterized by matrices, right? So we do not use matrices here, unlike MVRN. So it computes overall sentiment based on vector values for words and phrases it has been trained to recognize, right? So it actually gets the global sentiment of the words or the phrases, right? So that's the purpose. So words and the sub sentences. So to calculate basically the sub sentences and representations, we apply the compositionality function bottom up, right, using a tree structure. And we actually apply a softmax classifier for sentiment, right? So softmax classifier will be used with RNTN. So with recursive neural tensor network, RNTN was introduced, as I have told the beginning, in 2011-2012 by Richard Schlosser and from Stanford's NLP group. The authors introduced the recursive neural tensor network, which was trained on a different kind of data set called Stanford Sentiment Tree Bank. So they have their own data set built for this kind of network, and they actually trained the network on that data set. So Stanford Sentiment Tree Bank. If you search in Google, you will get to know what is exactly Stanford Tree Bank is, or I can, if time permits, I can show you at the end of this session that how they have a web page where you can actually write any sentence and it will form the tree structure and show it to you. So it's very interactive and very interesting. You can have a look for that. So another thing with the data, apart from the data set, right? So RNTN uses compositional vector representation for phrases of variable length and syntactic type. So for example, if you see here, right? So a example of recursive neural tensor network, it actually predicts these 5 different the sentiments, like for example very negative, very positive, or neutral, and positive and negative, right? So these are the things that can be predicted by these model. I mean, the sentiment tree bank has been formed in such a way that it will actually know that which are the words are very negative and very positive, right? So basically the structure of this RNTN recursive neural tensor network looks like this. So if you see here, as per the definition, right? So here are the output of the tensor product. So if you see here, RD is the output of the tensor product, and it adds an extra 2D into 2D into D D tensor to a RNN model, right? So with normal recursive neural network, we use a 2D into 2D into D tensor, right? That defines multiple bilinear forms. So it's little complex, and as it's meant to be. So from the research paper, right, it basically to understand this, so you should be knowing. That's why I have discussed about MBRNN and what is basically a recursive neural tensor rig. So it's a tree structure where we use a vector representation of the data or words that we feed into, right? And how we calculate the weight matrix here, we can basically see, right? So from the vector representation, if you look into that, v of I is a r of 2D into 2D matrix, right? So 2D into 2D tensor basically. So each slice of vector 1 is to D here, it is computationally being used as as my tangent function, right? F is the tangent function here, if you see. So after training each slice of the tensor, right, it captures a specific type of composition. So we get these as a slice to of the tensor layer, right? So and we have a normal or standard layer as well. So with a tensor layer, we apply a standard layer and we find the compositional from a particular sentence, right? So we have seen actually over 87% accuracy in positive or negative word classification, and with this using this network, and over 85% accuracy in positive and negative sentence classification, so on the Stanford sentiment tree bank. So they already I mean have been mostly trained in Stanford sentiment tree bank. And there is a parsing I mean parsing basically natural sentences or parsing neutral or natural languages, right, is a very effective algorithm to be used. And even for the sentiment analysis for Twitter data, a recursive neural tensor network can be used. So apart from this, I mean, we'll talk about the other algorithms that has been introduced later on, because this paper has been published in 2012, and there has been a lot of research and analysis has been done. But with core NLP toolkit, it is really effective and useful to be try on, right? So with RNTN recursive neural tensor network, right, so if you see intuitively, we can interpret each slice of the tensor as a capturing a specific type of composition. So here each slice, the purpose is to find out a different composition from each slice, right? So if you see here, the tensor, and with the standard layer, we can form a structure like this. So normally it looks like each node is assigned to a level by a softmax, and where W is the sentiment classification matrix. So if you see here, not very good with that, we have P1 and capital sorry, all are I mean going to the same. We do not have a matrix here, but we only have a vector and a tensor, right? So goal is to minimize the one more thing is here is scale divergence between the predicted distribution and at node I and the target distribution Ti at. So the error function of a sentence is here, if you see, we get the error function like this. And normally with the tensor backprop, right, so we try to find out the error functions of a particular sentence. And that's how we eliminate the minimal I mean the errors with the network, and find the compositionality, right? So one example, with the examples of positive negation, the RNTN correctly classified even if negation is less obvious in the case of list. So if you see here, a sentence with everything is same, right? Here Roger Dogger is one of the most compelling variations this theme. So here one thing, if you see, the least compelling and most compelling, right? So least is making the difference. So only for the least compelling variations this theme, it becomes, the complete sentence becomes negative, right? Again when we use most, it becomes positive. So this is one of the examples of negation that has been used with the RNTN. So RNTNs also learn the sentiment of phrases following the contrastive conjunction, but like dominate. So here if you see, these sentences are same, but there are contrastive conjunctions, right? For example, these schemes provide a solution to current traffic problems, but they are difficult to implement in their present form. Again, in the second sentence, these schemes provide a solution to current traffic problems, however they are difficult to implement in their present form. In the third, you have nevertheless. So by reading at these sentences, can we say which is positive or which is negative or which is neutral, right? So it is really these contrastive conjunctions makes the difference in the meaning of the particular sentence. So we with this capturing the negation, RNTN is very good at it, because it uses this tensor slices for each of the word and their compositionality, right? So the main advantage over the previous RNN model, which is a special case of the RNTN when V is set to 0, is that the tensor can directly relate input vectors. So intuitively, we can interpret each slice of the tensor as capturing a specific type of composition. So the model outperformed all previous methods, as I've told, on several metrics, and pushed the state of the art in single sentence positive negatives classification from 80% up to 85%. A more advanced version of this algorithm called tree LSTM was proposed by Christopher Manning in 2015, and we right now we have BERT and Elmo, right? So these are more advanced than these algorithms. And the tree LSTM model is generalized of LSTMs to tree structure network topologies. So one thing with the metrics, right? So RNTN handles the negations well. So the negations changes the overall sentiment of a sentence, right, from positive to negative. For example, the move was terrible and the movie was terrible, and the movie was not terrible says only that it was less bad than a terrible one, so not that it was good, right? So how a I mean, how much negation is there? How is it too negative? Is it neutrally negative? Or so what would be the value we can decide for a particular word or a sentence that changes based on these conjunctions, right? So that is that can be found using RNTN. So that is it is I mean it uh, um it is proposed that it handles these kind of negations very well. So if you see negated positive sentences with normally with RNN and MVRN and RNTN, so RNTN is better in the change in activation. And again, with the negative sentences, negative positive sentences if you see, and with the negative sentences, RNTN is very good. It is doing here in the is almost very high than any other algorithms being used. So change in activations for negations only the RNTN correctly captures both types. That's what the claim is here. And so we also can see that the based on the model, it actually captures the compositionality of negated sentences very well. So this is what the normal accuracy of a fine-grained 5-class and binary predictions with the sentiment. Basically, they use the Stanford tree bank. With that, we get this kind of accuracy. Okay, so conclusion of this session, right? So basically, which neural network you want to use depends on your usage. If your use case is to generate characters one at a time, so a current neural network is good. If you want to generate a phrase tree, right, or parse tree, sorry, so then using a recursive neural network is better because it helps to create better hierarchical representations. Based on the recent paper of semantic relation extraction, where long distance semantic dependencies play a role, recursive models offer a significant advantage, right? So also the recent algorithms like LSTM with recurrent attention, BERT seems appear to perform consistently well across the other sentiment classes. So you can actually check this paper, recurrent versus recursive approaches towards compositionality in semantic vector spaces. It will give you more idea about that why recurrent and recursive approaches are better, and what it does with the compositionality in semantic vector space. Now, so the whole purpose of this is to find the compositionality or the meaning between or in a word of a sentence, right? So with the LSTM, as I have mentioned earlier, right? So nowadays we can use attention. So that is kind of almost pretty much solves a lot of challenges with finding the meaning and compositionality at the global level. Earlier with the normal LSTM, we could not find the global compositionality, but with LSTM, if we use attention with BERT, normally it uses attention, we can find the global compositional or global meaning of a particular sentence. So that's all with this particular session. Let me know if you have any queries at the end of the sessions, and let me see if I can get you the sentiment tree bank that we can try with this particular example. Let's say for these, right? So let me
So audience, you can start putting in questions that you may have, and Indrajit would be willing to answer. I have not seen any questions till now, so please put in any questions that you have now.
So this is the data set that has been proposed by Stanford, and they have built almost, I think, 10 10,000 sentences or more. So this is the data set that they have proposed and they have trained the model on. And if you see a quick um, example of the sentences that I was talking about, what it can do from this um, website. So let's say if you open this, you would be able to find out. But still, I mean, I personally find there are so many shortcomings with the few of the sentences that it could not find. I mean, the website also says that you can suggest or improve the accuracy of particular prediction that it is making regarding a sentence, right? So that also can be, you can try that here. Um, let me open the session. I'm not sure if it is generally, it's a little running slow. So meanwhile, we can see the code here. So you can download the Stanford Core NLP toolkit, right? And also the data set given here. You can get that as well for test run. And one advantage with this is they have the releases available every quarter, I guess. So they actually modify this particular code and they ensure that we get this kind of the toolkit and the libraries is getting updated. So if you see here, it is the current version is 3.9.2, right? And you can download here with different languages. So I was trying to get the demo here. I had the link in the PPT, but I'm not sure if I have removed it. Yeah. We have some time. Meanwhile, you can pass in your queries. Not sure why it is not launching the page. I have tested it today morning. It was working. I ensured that they are not down. That's,
So one question, Indrajit.
yeah.
So which one is better, RNTN or LSTM?
So of course, if we use LSTM with, as I told, right, if we use LSTM with attention, it is much more better. I mean, the publisher actually proposed that LSTM with attention is much more accurate. So the paper that I have mentioned at the end of this session, you can have a look into that. So they have a combination and comparisons with the recurrent and recursive, and they actually talk about LSTM and with the BERT, what exactly is the modifications and how far they are doing good. Now, we cannot actually say that a particular algorithm is much more better, because it exactly I mean it depends on the use case and the data that you have, right? So if you have a very let's say a kind of social media or contextual meaningful data, you need to find the meaning. It is, of course, RNTN is doing better with the negative or negated sentences, right? So there could be something where you just want to find that summary or summarization of a particular corpus. So in that case, LSTM with attention also will do better, right? So it's completely on the context that you are trying to get out of a particular corpus or document. Okay.
Thank you. Another is, can we use this approach to predict it next diagnosis of member?
Uh, can we clarify the question? Can we
I'll
predict?
repeat.
Yeah.
I'll repeat. Can we use this approach to predict next diagnosis of member?
Next diagnosis of a member. Okay. So basically on the, I think the user intends to get medical data and want to find out that what could be the next. I feel with with basically the predicting that what exactly to be done. Let's say I'll give you one example. So in mathematics, let's say I want to find the prime numbers, right? Given two numbers, 10 and 7, and want to find out whether which number is prime, right? So to find out the meaning and what exactly is it actually it mean to, whether it is just 10 and 7 is the number that the sentence is talking about. If my network is able to understand it, that's what my purpose is. So if I am able to understand what this sentence is
You're
mean
not
to, I
audible.
can am I audible?
Indrajit, you are not audible.
Okay, let me see.
Can you please repeat?
Am I audible now? Is it
Yeah,
better?
yeah, yeah.
Okay, okay. So with the sentences, right? So I was giving an example. So if a particular question is like that, and find the prime numbers between two numbers, and if I'm able to extract the meaning or able to find out what exactly it means, is just only asking about two numbers, or it is asking me to find the prime numbers. So what is a prime number? What is the knowledge behind it, right? So that is kind of still a challenge that we are trying to solve. So with the medical data or anything where we want to find the diagnostics, or we want to predict that what could be the answer for a particular question. So a patient can mean a particular say we can have an example like is having a knee pain, or let's say right chest pain. So it with whether that means something with high blood pressure or some other related diseases, right? So obviously it is again, I feel it's a more challenging, or we need to actually try on with the data, and we should find out that how much meaningful information it can extract.
Okay. Any other questions? So we still have 5 minutes to go. So if you have any more questions, please ask.
Sure.
So you are done with your presentation, Indrajit?
Yeah, Vishal, I'm done with the presentation. I
Sure.
think there is this, it would have been better, but I would say this is a open source, so people can go ahead and try this once it is available. So it is not probably not running now. Okay, so that's all from my side, and thank you everyone for joining. Thanks for your time.
Sure. So any other questions if you have, you can ask now, or I'll show. Do you have your contact details, Indrajit, there? If people can would like to contact you.
Yeah, so I can give my one moment. So I think I did not put it here in the slide.
So no issue. So what I'll do is I'll take back the presentation
Yeah,
and I'll show my contact details. If people want to ask any queries, they can route it through me.
sure, Vishal. Thank you.
Sure. So people, you can send queries on this number or email address. I'm also on WhatsApp on this number. So if you would like to have any queries answered through Indrajit, you can put them to me and I will get those answered through him. And we also have a WhatsApp group on Disrupt 4.0 where we share a lot of such content on daily or alternate day basis. And so if you would like to be part of it, you can send a message to this number on the screen and I'll add you there. And look forward to have you in future webinars. Since I'm not getting any more questions here, so we would like to, we will end the webinar now. It's almost 1. So thank you, Indrajit. Thank you for giving the webinar and look forward to more such sessions from you in the future.
Sure. Thank you, Vishal.
Thank you and have a good day to all.